Hey everyone, and welcome to this explainer. Today, we're not just looking at pretty landscapes, we're actually going to look at the Earth as a massive, super dynamic machine. Think of it like a giant engine governed by fluid dynamics, solar radiation, and the literal rotation of our planet. And the exhaust from this planetary machine? Well, it creates some of the most extreme, unforgiving environments on the globe. We're talking about vast regions that are defined entirely by one thing: scarcity.
Okay, let's dive into this. 30%. Now you might be wondering what that means. That staggering figure actually represents the amount of Earth's terrestrial surface currently covered by deserts. 30%. That is nearly a third of all the land on our planet, and it's defined by a distinct lack of moisture, where evaporation vastly exceeds precipitation.
Which brings us to the central mystery we're unraveling today. What do the scorching hot sands of the Sahara and the freezing ice of the Antarctic actually have in common? I mean, our instincts tell us they're polar opposites, right? But geologically speaking, they are basically twins. Both of these extreme landscapes are deserts. You see, they aren't defined by their temperature, whether they're blazing hot or freezing cold. They are defined by a severe, almost total scarcity of precipitation.
All right, part one, the global atmospheric engine.
Now, what's really interesting about this slide is how it shows the invisible architecture of our sky. The Earth is heated unevenly. Solar energy hits the equator directly, causing warm, moist air to rise. As it goes up, it cools off and drops its moisture as heavy tropical rain. But that dry air has to go somewhere, right? It gets pushed north and south, eventually sinking back to Earth at around 30 degrees latitude in what we call the Hadley cell. This sinking, bone-dry air creates intense zones of high pressure. And wouldn't you know it, that's exactly where we find the Sahara and the Australian outback. A very similar process happens up at the poles, where freezing dry air sinks in the polar cells, creating literally the driest deserts on Earth.
But the air doesn't just travel in a straight line north and south, because, well, the Earth is constantly spinning. This brings us to the Coriolis effect. As the planet rotates eastward, it deflects these moving air masses. This planetary spin is what generates our prevailing trade winds and westerlies. And when these prevailing winds smash into mountain ranges, we get rain-shadowed deserts. The wind forces moisture-heavy air up over the mountains, where it rains out. By the time that air descends on the other side, it's completely tapped out. Combine this rain shadow effect with descending air and cold ocean currents, and you get places like the Atacama Desert in Chile, the driest non-polar location on Earth. There are literally spots there that haven't seen a drop of rain in years.
Moving on to part two, shaping the arid sands. And this brilliantly illustrates the microphysics of wind erosion, specifically a process called saltation. You know, wind doesn't usually just blow sand in a perfectly straight line. Instead, the sand grains are lifted slightly, blown forward, and then they drop, splashing back into the surface and dislodging other grains. It's this cascading, bouncing movement that happens in a zone just about a meter above the ground. This bouncing action acts exactly like a giant sandblaster, slowly eroding solid bedrock into these wild, unique shapes. Notice how this totally differs from finer silt and dust, which actually gets suspended high up in the air, creating those massive, towering dust storms we call haboobs. Wind is just an incredible sorting machine.
So, when that wind-blown sand finally accumulates, we get ergs, or sand seas, and the formation of dunes. But the geometry of a dune isn't just random. It's a direct readout of wind direction and sand supply. We've got Barchan dunes, which are shaped like crescents and form where sand is limited, but the wind blows in one constant direction. Then there are longitudinal dunes, forming these massive linear ridges from back-and-forth winds. We see parabolic dunes, which are locked in place and anchored by sparse desert vegetation. And finally, star dunes, which peak and branch out in multiple directions because the wind in that area is highly variable. The landscape is literally a recorded history of the wind.
But surprisingly, wind isn't the only sculptor out here. When rare, intense rain does fall in the desert, it transforms the landscape violently. Desert soil lacks organic matter. It's basically baked into a hardpan, making it hydrophobic, or water repellent. So instead of soaking in, actually, scratch that, it doesn't soak in at all, the water instantly becomes runoff. This triggers massive flash floods that absolutely roar through dry canyons. As this huge wall of water and debris exits the narrow canyon and hits the flat valley, it abruptly slows down and dumps all its sediment, creating these fan-shaped deposits we call alluvial fans. When multiple fans merge together, they form a bajada. And if that water gets trapped in an enclosed basin, it eventually evaporates to leave behind perfectly flat, extremely salty dry lake beds called playas.
So, yeah, water is scarce, but when it's there, it is a dominant geological force. Let's switch gears. Part 3, Frozen Deserts of Ice.
So, glaciers only form in places where more snow falls in the winter than melts in the summer. It all starts out as perennial snow. As the years go by, new snow piles on top, compressing all those older layers underneath. The void space between the snowflakes shrinks down, turning it into a really dense granular mass called firn. Over even more time and under immense pressure, that firn recrystallizes into solid glacial ice. It's this incredibly slow, relentless transformation from delicate little flakes into literal solid rock.
So the crucial point is how this solid ice actually moves. A glacier isn't just a giant ice cube sliding down a hill. The top 50 meters is what we call the brittle zone. It's rigid. As the glacier moves, this top layer fractures and cracks, creating incredibly dangerous super deep crevasses. But below that 50-meter mark, something absolutely amazing happens. The sheer weight of all the ice above it pushes the pressure past 100 kilopascals. Under this extreme force, the ice stops breaking and actually starts bending. It enters the plastic zone. Deep inside, the solid rock ice is literally flowing like incredibly thick plastic.
Okay, Part 4, Carving Glacial Landscapes.
You can almost immediately tell if a landscape was shaped by water or by ice. Liquid water in a river cuts straight downward, creating deep, narrow, V-shaped valleys. But a glacier doesn't just cut, it bulldozes. It completely fills the entire valley, grinding against the floor and the walls. The result is a really distinct, wide U-shaped valley. And when multiple glaciers carve into the exact same mountain from different sides, they leave behind these incredibly jagged, spire-shaped peaks known as erosional horns.
And as a glacier acts like a bulldozer, it also kind of acts like a giant conveyor belt. It plucks up rocks, sand, and massive boulders, carries them along for the ride, and then dumps them. This unsorted, messy mix of debris is called till, and the mounded deposits it forms are called moraines. We can literally map a glacier's history just by scanning these moraines across the terrain. Terminal moraines mark the absolute furthest advance of the ice. Recessional moraines show exactly where the glacier paused during its retreat. Lateral moraines run right along the valley walls. Medial moraines form ridges right down the center where two glaciers merge together. And ground moraine? That's just the uneven layer of till left behind as the whole entire system melts.
But get this, here is a truly surprising depositional feature, the esker. Even beneath kilometers of solid, bone-crushing continental ice, liquid water is still doing its thing. Meltwater descends through the cracks and forms these high-pressure rivers flowing completely under the glacier. And these subglacial rivers carry a lot of sediment. So when the ice age ends and the glacier melts away, the sediment that filled those underground riverbeds is just left sitting there on the landscape as these long, sinuous, snake-like ridges. It's wild to see.
Let's move to and see how this builds into Part 5, Climate Cycles and Rebound.
Historically speaking, massive ice ages have been driven by Milankovitch cycles. These are basically subtle shifts in Earth's eccentricity, its obliquity, and precession that change exactly how solar radiation hits our planet. When these orbital cycles shift and the glaciers start to melt, two massive planetary changes kick in. First up, we have eustatic sea level rise. As land-based ice melts, all that extra water runs straight into the ocean, physically raising the global sea level. But secondly, we have isostatic rebound. Continental ice sheets are so incredibly heavy that they actually press the Earth's crust down into the mantle. When the ice melts and that immense weight is finally removed, the land slowly springs back up. The continents literally rebound.
Now, the source material provides some very specific data on the current state of these ice sheets. Based on satellite telemetry, this outlines the current annual ice mass loss. The data shows Antarctica is losing roughly 118 gigatons of ice per year, while Greenland is losing about 281 gigatons annually. The texts indicate that this rate of ice mass loss is unprecedented in the modern observational record, which goes back to the 1940s, and it's contributing rapidly to eustatic sea level rise as a result of anthropogenic warming.
And this timeline really helps put why this all matters into perspective for us. Earth's climate is a super delicate balance. Just 19,000 years ago, during the last glacial maximum, so much water was locked up in ice that global sea levels were 125 meters lower than they are today. Fast forward to the 1930s, and we see the Dust Bowl, a really harsh reminder that human activity can rapidly accelerate desertification, turning perfectly arable land into a totally arid wasteland. Today, we're witnessing the opposite end of the spectrum, with rapidly retreating ice sheets threatening coastal areas worldwide.
Both extremes, whether it's way too little water or way too much, completely reshape where and how we can survive.
Which leaves us with this final, incredibly critical question to consider. As the planetary machine continues to run, as temperatures warm up and sea levels rise, how is humanity going to adapt? We are firmly caught between the expanding deserts of sand and the vanishing deserts of ice. Understanding these immense, slow-motion forces of fluid dynamics and geology isn't just about knowing our planet's past. Honestly, it's the only way to prepare for its future. Thanks so much for joining this explainer. Keep questioning and keep exploring.